with the symbol A, they do fulfill, when you have an annihilation and creation operator, you have delta functions here, and if you have the same type of operators, the anti-commutator is equal to 0. In the case of bosons, the same kind of relations hold, with a big difference, of course, that here we have to take the commutator and not the anti-commutator. Finally, it will be important that, of course, bosons and the fermion operators are different, and so they fulfill commutation relations equal to 0. Yeah, they commute with each other. Now, behind this anti-commutation and commutation rules is the Pauli principle, saying that fermionic should have antisymmetric wave functions, and or saying in this commutator exactly says that you cannot have two fermions occupying the same quantum states. And of course, for bosons, it has to be symmetric. Now, in general, if you want to describe now in this interacting boson fermion model, odd A nuclei, your Hamiltonian splits in three parts. You have the boson, so to say, core part, which is the normal IBM1 Hamiltonian. Then you have a pure fermionic part, which generally is the single particle or quasi-particle energies multiplied by the number operator for the fermion in orbit J. And you have a boson-fermion interaction. The most general boson-fermion interaction is quite complex, because you have to create a boson, create a fermion, and then to annihilate a boson and to annihilate a fermion. And then you have to do all possible couplings to J, and then here also all possible couplings to J. And then, of course, it has to be a scalar, so you have to couple to 0. So it means that you have these possible coefficients here. They will be very numerous. So now we are complete. So there will be many of these coefficients, and this is, of course, not something you can then take as a kind of phenomenological fitting parameters. There are too many. Remember that generally, if you do a good calculation, you will allow the fermion to occupy about 5 orbits. Yeah, 5 orbits with different J values, and that you all have to couple in all possible combinations. And so this is not a practical way of doing structural description and taking this as parameters. In fact, in the shell model, you do that more or less. You have the matrix elements, and you calculate, for instance, or you fit 64 matrix elements to a given number of nuclei, and then with this matrix element, you try to describe now a whole shell, so to say. So in principle, you could do such a thing here, but that is not done. Also, I would like to remark that you need to change the annihilation operator in order to provide a good angular momentum coupling. And again, this is changing the M index. You have a phase factor here, and you change the M index. Now, the most general Hamiltonian contains much too many parameters and is replaced by a much simpler one based on shell model consideration and on PCS calculations. So Bardeen, Cooper, Schiefer, that's from superconduction. So such a kind of go to quasi-particle is done also in the interacting boson model. Now, if you do that, then one considers only 3 terms, with still a lot of coefficients, but we will see that these coefficients will be determined partially from the BCS calculations. So the first term is a monopole interaction. So here it's written in another way. We take the boson parts together and the fermion parts together, couple them to 0, and then of course the total is coupled to 0. So that's the first interaction. The second one is the quadrupole interaction, where you take the bosonic quadrupole operator and you couple the fermions to two. Of course, you have several orbits, so you have several coefficients here, which are possible, and then, of course, the whole to zero. The third interaction is an exchange interaction. And this you can see here, these are possible exchange interactions. I can decouple the two nucleons of orbit J coupled in an S boson and take the unpaired nucleon and then recouple it to make an S boson. Or I can do it with the different values of J to couple into a D boson. Yeah? And so on. I can go from a D boson, exchange with the uncoupled nucleon and make an S boson. The only term, yeah.
Why do you say always? It's of course coupled to zero.
Because Hamiltonian always has to be a scalar.
Mm-hmm.
That's also used in our model. Yeah, you don't have to specify that your Hamiltonian is coupled to zero. Yeah.
But is not that angular momentum coupling?
Yes. Yeah.
But can you have interaction? Like can you couple to something else and then sumo over this index as well? For example, you couple to.
No, the couplings are inside here. They are not here. The total has to be a scalar. Except if you would do experiments in magnetic fields, then of course you will get a splitting for the m values.
Yeah. Otherwise, it's sensitive.
Yeah, but we always consider scalar to operators to O3, yeah? So that they have a good J quantum number and that the magnetic states are the same. Now, from microscopic and shell model arguments in the interacting boson model, only the last exchange interaction is taken into account. Yeah? But also here you have a lot of parameters which are possible. Now,
sir,
yes?
sir, can you go to the previous slide? Sir, can you please explain the last pictures, how to couple these things? S boson.
The last one.
No, no, means the fourth.
Eh?
Yeah, four of them.
No, so let's start with the one we will consider here. Yeah?
Okay.
We have a D boson. Now I can make a D boson out of coupling J double prime with J triple prime to 2. Yeah? Then I have a D boson. And suppose my uncoupled one has another orbit, J prime.
Mm-hmm.
But J prime, if you couple it with J triple prime, can also make a 2.
Okay.
Yeah? Then you can have an interaction in which the D boson now just recouples to J prime, releasing J double prime.
Mm-hmm.
Yeah? And so that's, the notation is a little bit smaller here. So you can, because they are grouped in another way here, so it means that you can couple 2 and G prime to G double prime, and D and G to G double prime, and then the easy intuitive picture is here. Suppose I have 1/2, and here I have 3/2, and I have 5/2. So 3/2 and 5/2 I can couple to a D boson. But I can also couple 1/2 and 3/2 to a D boson. And so the interaction is the one in which you change the coupling of one of the D bosons going over from a 5/2 to a 1/2, coupled to a 3/2. Now still, this number of coefficients is much too big. And in order to reduce that, a BCAS calculation is done. It gives quasi-particle energies and occupation numbers U and V as a function of the single particle energies and the pairing gap. So here you have single particle orbits. You can put then nucleons into these orbits, yeah, fill up the orbits. But you can now go to the quasi-particle description with this kind of pairing gap, and you get a kind of Fermi distribution over the probability that the nucleon will occupy one of these orbits. And so that gives these occupation probabilities and also the quasi-particle energies. They are different slightly. And then using microscopic arguments, the terms kappa y turn out to be just one constant parameter, BFM. The terms kappa y prime from the quadrupole is also a constant parameter, is a function of the u's and the v's of the different orbits and the matrix element, reduced matrix element of the spherical harmonic of order 2. And finally, this this more complicated kappas turn out to become also one parameter, BFA. There's also a reduced matrix element, but now twice. There are some combinations of U and V's, and there is here still an energy term. These are the quasi-particle energies. Also in the fermionic interaction, you now have the quasi-particle energies. And then there is a term, H bar omega, which corresponds to the first excited 2+ state in the corresponding semi-magical nucleus. Now, we have reduced the number of parameters enormously in this, so to say, semi-microscopical model. So if we look, we have now n single particle energies, in this case 5. We have the gap delta, because this is the only input. This you can take from experimental data. The gap you can estimate, and this yields all these U, V's, and these quasi-particle energies. Yeah? So it's not so that you have now for 5 orbits and then I have to fit 5 U's and 5 quasi-particle energies. No, I start with 5 single particle energies, 1 gap parameter, and I fix with that large part of this Hamiltonian. And this I can also take from experiments. So we have done 3 parameters in order to describe the boson-fermion interaction, and we have 6 parameters for the boson part. So this is the essence of Olaf's thesis and also of the ODA code which he wrote.
Sir,
Yeah.
what does it mean by the semi-magical nucleus?
Semi-magical, it's the one, if you have an odd proton, then you go up till the closed shell, the nearest closed shell, and you look at the energy of the 2+ state.
Okay, there is just one particle minus the actual nucleus. Just you remove the one particle, then...
No. This is just the excitation of the first excited 2+ state. For instance, if you would describe odd indiums,
Okay.
then the next closed shell, semi-closed shell, would be tin. Yeah?
Oh,
And then you go to indium is 1 proton below tin, then you just look in tin, then you have an even nucleus for the energy of this 2+. And that's determining this parameter H bar omega. So, well, this is the ODA code, which still is in use. I show one example from my PhD work is the calculation of odd rhodium isotopes. So I took first of all the boson part from fit made by Piet van Isacker before and published before. So that fixes, rhodium is below palladium, so this fixes, so to say, the even core, or the boson part of the Hamiltonian. And now if you look, then there are 5 orbits of different parities which are taken into account. You have especially from transfer reactions and studies, you get the single particle energies for these orbits from the literature. Maybe you adapt it slightly in order to improve the description. Then you do the pairing calculation with this parameter delta, which is 1.5 MeV, and this gives you then the quasi-particle energies and the occupation probabilities for the different orbits squared here. U y squared plus Vy squared should sum up to 1. Yeah? So from that you can extract also the parameters U, J. Now, if you do that, then you can describe with one Hamiltonian, these are the parameters, the three parameters, you can describe with one Hamiltonian the positive parity states in these rhodium isotopes. But can we put this out? Mhm. Okay. Now forget. Yeah. Okay. So you can describe the positive parity orbits coming from the D and the G orbit, and the negative parity orbits coming from the F and the P orbits. So here you compare to reasonably high energy the experimental data and the theoretical data. But you can do much more. One, I'm sorry, I don't have it here for the rhodiums. One important quantity are single particle transfer reactions. So, which corresponds to, in a model, to the creation of a fermion starting from an even core. And so, also these quantities you can calculate. We will see that later on, especially in the second lecture.
Excuse me.
Yeah.
Can I ask a question? So, could you go back to previous slide? So, I'm interested in how affect the exchange part. So,
The exchange
yeah,
part.
if you turn off the exchange part,
No, the exchange part is important. The one which is the least important is the monopole part. Because, okay, it's also important. It's a scaling factor. By the monopole part, you will just more or less extend or compress the spectrum. Yeah? But in the exchange part, it will be important to change the sequence of spin states, like the quadrupole part. If you look, maybe here, if you see, you have 9 plus, 7 plus, 5 plus. And then the 5 plus is going down, 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 down. These are typical things which are caused by the quadrupole and the exchange part. Yeah? And I would like to mention one thing. This calculation, these are 1, 2, 3, 4, 5 odd A nuclei, the positive and the negative parity states. And then you might say, yeah, this is a lot of parameters, but they are constant. Yeah? So they are constant in this calculation. So the deal of what you can describe, if you do more than one nucleus, is reasonable. If you do only one nucleus, you have, of course, the problem that you might have a little bit too much parameters. Yeah? And also, I would like to mention again that these values are taken from Kisslinger and Sorensen, so from the literature, and also this value is taken from the literature. The boson part is taken from the literature, and so then the number of free parameters is not so big. But again, you have a little bit of problem that you need to do a series of isotopes. Now,
Jan,
yeah.
do you have a working program or that?
Yes.
Yes, because some
Not
people-
here.
No, but I mean, some people are interested in odd rhodiums and, I mean, these odd nuclei in this region.
Ah, okay. Yeah.
But my other code is not working anymore, so maybe
Yes. Yeah.
okay, they can contact you and
I think I have all IBM codes open.
okay.
I think I gave you 15 years ago or so. Already one.
Yes, maybe.
Yes. Now, our interest is in symmetries in atomic nuclei, and so now the question comes: how but what I showed you before is a semi-microscopical calculation where you don't care about symmetries, but we like symmetries. And so the question is, how can we now introduce symmetries in a system made out of bosons and fermions? So I recall you the intuitive picture where we have S&D bosons and we have the U6 symmetry for the model space. So intuitively you can see these generators, there are 36 of them, and they just shuffle around if you do a basis transformation between the different bosons with their magnetic projection. So we had 36 generators. Now if we have NSD bosons plus one or more fermions, then our symmetry will be UB6 from S&D, and then I consider first the case that you have only one orbit. The degeneracy is 2J plus 1, so you will have unitary transformations in a 2J plus 1 dimensional space. If you have more orbits, you have to make the sum over the different degeneracies of fermions. Now, the logical thing is now to do a kind of block structure. We extend our 36 generators and add 2J plus 1. In the vector, we add 2J plus 1 projections of the fermions. And then we get here the generators of the fermions. They are creation and annihilation between different magnetic substates. Sorry, I've forgotten to put the index n here. And then we have a block structure. Bosons only transform among themselves, and fermions only transform among themselves. And this block structure we see here in the product of the two symmetries. So the U6 algebra times the U2J plus 1 algebra. So the number of generators are now 36 boson generators plus 2J plus 1 squared fermion generators. And the important point is they both couple to integer spin. Yeah? So if I couple fermion creation 1/2 with fermion annihilation 1/2, I get either 0 or 1. But the important point is each generators couple to integer spin if you do an angular momentum couple. And because of that, they fulfill the standard Lie algebra conditions. Yeah, we will see in more extended cases we will have non-standard Lie algebra conditions. But either whether you have, let's take the example which is maybe the most logical to show this, whether I have a 5/2 fermion, then I have UB6 times UF6. Both have a unitary transformations in 6 dimensions. However, the B refers that it's made out of bosonic generators, those, and the F refers that it's made out of fermionic generators. And don't think that if I have UB6, UB5, UB05, UB03, that I will also have a possibility to have UF6, UF5, UF05, and so on. No, not possible. And the reason is that you cannot find the same subsets of generators in the bosonic case as in the fermionic case.
In the fermionic case, the Lie operation would be anti-commutator.
The Lie operation. No. Okay, good for your remark. The fermions anti-commute.
Yes.
Yeah. I just mentioned, extremely important is the generators coupled to integer spin. The Lie commutation rules of closure hold for the fermion generators exactly the same as for the boson generators.
And then don't we have the same subset then?
No, because you now have to find subsets which close on the commutation amongst themselves. Take the example, because this is an important point. If I take the example of J5 half, yeah? Remember how we constructed the U5 limit? We took out the S boson and only kept the D boson generators. How can I do that now with 5 half? It has 6 magnetic substates, so I could take out one of these magnetic substates and then say the other will commute among themselves. They don't. Yeah? So the kind of structures is different. That's important to see. They both form Lie algebra. The generators are bosonic type, so to say. They couple to integers spin. So the conditions for the Lie algebra are exactly the same. Yeah? But in order to make subsets, you have to look at the generators in detail. Yeah? So you cannot transform one subgroup to another one. Then, in fact, in the literature, it happens that people do that, and it's completely wrong. There's an easy way to test it. You put in one fermion or one boson, and then you do the reduction rules. And if you started with a D boson, you have to end up with L equal 2 as spin. And if you start with a 5 half fermion, you have 5 half. But there are cases where you do the reduction and you end up with something completely different. So, but that's a good test if you want to construct a symmetry. Okay, now, so examples of boson-Fermi symmetries, yes?
But isn't the reduction of the dependent on the group, doesn't like unrepresented generator at a fermionic over one? I make linear combinations of fermionic and make the ability to be higher.
We will make a linear combination in cases where the groups are isomorphic and the least structure constants are the
I
same.
was just going to ask.
Yeah.
I don't think the group for the bosons is isomorphic to the group of the fermions. Could you find are they isomorphic?
There are cases, they come now. But it's not UB6 is isomorphic to UF6.
It's not. They're not isomorphic.
No.
Okay. Yeah.
In some cases you can do tricks. We will come. There are two kinds of tricks. I will explain them now. So, two types of boson-Fermi symmetries have been constructed. The first one are spinor and pseudo-spin types. Now the spinor types, they use this isomorphism between bosonic and fermionic groups. As an example, you know this example, SO3 and SU2. Yeah? SO3 describes orbital angular momentum, but SU2 describes spin. And you can combine both orbital and spin to total angular momentum, which will be part of SU2. Yeah? So that's one example of this kind of spinor type isomorphism. And generally you can call it spin 3. The next one which exists is spin 5, and this is SO5 being isomorphic to SP4. And finally, there is another one which is called spin 6, and this is SO6 being isomorphic to SU4. Now, interesting is that these three groups occur in the interacting boson. So I can take as an example, this was done by Palantikin, Bars and Iacello in 1981. You take an SO6 core and a J3 halve fermion. 3 halve makes U4. So you start with U boson 6, U fermion 4. Here you have n bosons, here you have 1 fermion. And then you can do the reduction to SO6, giving the sigma quantum number. And you can reduce also U4 to SU4. And now these two are isomorphic. So it means that you can combine now the generators such that they close again under commutation and form a Lie algebra where they are combined. The generators are, in some sense, linearly summed. This group we denote now by spin 6. If you look at SU4, you had already 3 labels for fermions. So now you have 3 labels for the spin 6 quantum numbers. You will have 2 labels for the spin 5, which is O5 is a subgroup, and SP4 is also a subgroup of this. And then SU2 is a subgroup of this, and O3 is a subgroup of O5. So you can do this combination spin 6, spin 5, spin 3. So the Hamiltonian, which does not only contribute to the ground state, these terms are just contributing to the ground state, is this term, that's also a constant term. So we have A, Casimir of SO boson 6, and then Casimir of spin 6, Casimir of spin 5, Casimir of spin 3, with 4 parameters. And again, this is a dynamical symmetry, and we have a general analytic expression for the excitation energies in these Bose-Fermi symmetries. Now, this is the result of such a Bose-Fermi symmetry, and it looks like that. That's the spin boson-fermion 6 symmetry. You have a 3-half ground state, which is what you would expect. If you couple a 0 plus and then a 3-half particle to it, then you get a 3-half ground state. It becomes different higher, because if you couple a 3-half to a first excited 2 plus, then you would expect 1/2, 3/2, 5/2, 7/2 multiplet in weak coupling. But we are not dealing with weak coupling. We're coupling here at the level of O6, spin 6, and not at the level of spin 3 or O3. And so we see the spectrum here becomes already different. So this is not a weak coupling spectrum of the 3/2 to the core. In fact, the 3/2 which one expects here comes here with other quantum numbers, and also here this is not completely following weak couplings. So these are the spin 6 quantum numbers, these are the spin 5 quantum numbers, and these are the angular moments. Now the second type is of pseudo-spin type, and this uses pseudo-spins to couple bosonic and fermionic groups together. Example, most famous is J equal 1/2, 3/2, 5/2 for a fermion. It was constructed by Pete, Alejandro, and Sun in the beginning of the 80s. And what you do is you have L0 and L2 for the bosons, and then you have 1/2, 3/2, 5/2 for the fermions. But now you can recouple these fermions out of a L equals 0 and L prime equal 2 part, coupled with an S prime equal 1/2. Yeah? If I couple 1/2 with 0, I get 1/2. If I couple 1/2 with 2, I get 3/2, 5/2. So in group reduction, we have a total dimension here of 6 plus 4 plus 2. So we have dealing with a U12 group for the fermions. That's the sum of the magnetic degeneracies. We are dealing with a U6 group of the bosons, and this pseudo-spin coupling reduces U12 to U fermionic 6 for 0 and 2 times U fermionic 2 for 1/2. And because these are pseudo spins, equal values as the spins of the bosons, they have exactly the same commutation rules. The fermionic generators of these pseudo spins and the bosonic generators of the bosons. They have exactly the same commutators. It means also Lie group constant, so you can just linearly add both. And if you do that, then you combine the boson 6 group with a fermionic 6 group to a boson plus fermion 6 group. Why a boson plus fermion? Because now the generators are a linear combination of the bosonic generators and the fermionic generators. Of course, you're left with a pseudo spin 1/2, so that's always staying here. Now, because we have now a U6 boson plus fermion symmetry, we can reconstruct the U5 limit, the SU3 limit, and the SO6 limit, then still coupled with this pseudo spin, but at the O3 level, we can now go over and couple 1/2 to the states in a kind of recoupling and go over to spin 3. So that's the second type which one can use to construct boson-fermion symmetries. Again, this leads, like we had in the IBM 1, to a general Hamiltonian which now contains about 8 parameters plus a constant as possibilities, and this Hamiltonian has analytic solutions provided you are in one of these symmetries. But it also can be used to describe transitional regions. So example which we will use and study quite some times in this today is a O6 limit of the U6 times U fermionic 12 boson-Fermi symmetry. So again, here you use the trick with a pseudo spin to get the fermionic 6 times the fermionic 2. Then you combine both generators linearly, get the same Lie structure constant to get this boson plus fermion group, and then you go to the SO6 limit, and now you have 2 labels for the quantum number, and you continue like that. You have 2 labels like in the IBM 2, which Norbert Petralla was telling about. And in fact, historically, this supersymmetry preceded the F-spin symmetric limits of the IBM. It's based more on this tricks that it was applied to IBM 2 than the inverse, which many people believe. So you continue then with O5 and then O3, and then you couple the pseudo spin to it to get a spin shape. The Hamiltonian in this case has 1, 2, 3, 4, 5, 3 parameters which you can adapt to the spectrum. Now, if you look at the result, so it starts here with 1/2, and then 3/2, 5/2, and then it goes up, and there are these pseudo spin doublets, yeah, because you couple at the very last moment, you couple to the combined boson plus fermion system. Because you have many orbits, you have 3 orbits, you have many states. So you see there are a whole classes of states which are calculated in this boson-Fermi symmetry. And some have this double representation, some have single representation. Now, question is, can we go further? And this is possible, was introduced again in the 80s, and it's called a dynamical supersymmetry. So, supersymmetry in particle physics deals with space and time. So, this is not what we are dealing with. We are doing this dynamical symmetry, which describes the dynamics of a Hamiltonian using symmetries. And so we are dealing here with dynamical supersymmetries. Or the question is, can we connect atomic nuclei using supersymmetry instead of normal symmetry based on Lie express? So the question is yes, and that was proposed by Franco Iachello in 1980. We can introduce supersymmetry by introducing new types of generators. Generators which annihilate a boson and create a fermion, or annihilate a fermion and create a boson. And such systems are described by supersymmetries, not by normal symmetries. So how can you intuitively see what is happening? Remember, I had here my vector. The upper part were bosons, the lower part were fermions. In the boson-Fermi symmetry, this block was 0 and this block was 0, and so I didn't mix bosons and fermions. Now, if I add to the matrix these off-diagonal elements, consisting of annihilating a fermion, creating a boson, yeah? So if I take this vector, then I annihilate a fermion and create a boson, so I end up here in the upper sector. Or annihilating a boson and creating a fermion, so moving a boson from the upper sector to the fermionic lower sector. Now the number of generators is 6 plus 2j plus 1 squared. And again, the important point is these generators are now of fermionic type. If you couple a boson with a fermion, you get half integer spin. And also here, you have half integer spin generators. And there are no Lie algebra generators. Because the commutation rules between those are not closing, or there are commutation rules between those which are not working, and between those they are not working. So it's clear that such a system cannot exhibit a Lie algebra. Yeah.
So what is your motivation to start this? Because you're destroying, for example, 2 neutrons creating 1 proton, or destroying 2 neutrons or creating 1 neutron. So with this statistic, with this model, you're trying to describe not only 1 nuclei, but 2 nuclei.
Yeah.
Nuclei
Exactly, that's exactly.
all
We
around
are-
it.
We are trying to describe in this instance one even nucleus and one odd A nucleus with one hamiltonian. I will come to this point.
Okay.
Yeah. So that's the motivation. Now, in the 70s, the concept of Lie algebras was extended to graded Lie algebras or superalgebras by now having for the combination of bosonic and fermionic generators a combination of commutation and anti-commutation rules under which they have to close. So this is done and motivated by particle physics. It's called supersymmetry. You heard about superstring and things like that. That's all using supersymmetry. It looks at the moment that there is no supersymmetry, or that next year CERN will find out that there, unfortunately, is no supersymmetry. But the whole, when I was a PhD student, I think 1/3 of all theoreticians in physics were working on supersymmetry. That was a quote which I read. I was also working on supersymmetry. So this concept has turned out, as I said, not to be so successful for what it was built, particle physics. They didn't find any super partners yet. It would solve big problems in the standard model, but we have to see next year whether it will be confirmed. But at the same time, other applications of super algebras evolved, were in mathematical physics, supersymmetric quantum mechanics was developed, and so in nuclear physics, these dynamical supersymmetries were developed. Now, the graded Lie algebras have another notation than the standard Lie algebras. They are denoted by U, and then in the brackets you have the bosonic part / the dimension of the fermionic part. And also the quantum numbers are denoted by a new symbol which more or less symbolizes that is a combination of commutator and anti-commutator rules. Yeah? And so now, if we remove from our superalgebra these two blocks, then of course we have a set of generators. It means that if we have a reduction from the supergroup U6/M to the product group U bosonic 6 times U fermionic M. The total number of bosons and fermions is the representation of the supergroup. And that reduces them to the total number of bosons. And here, in order to indicate that the Young tableau is vertical, 1 to the power of the number of fermions. Yeah. So the reduction rule is very simple. It's a little bit what Fazil was mentioning. You are changing the number of the actual nucleus. You go from an even nucleus with n bosons to an even nucleus with n minus 1 bosons and 1 fermion. And that's another method. But that's in fact what you want. You can see it here. What is the effect of the introduction of the supergroup and the superrepresentation? If you follow the reduction rule, so then here you have this n minus 1 times 1, you continue through the Boson-Fermi symmetries and you end up with a level scheme of an odd A nucleus. If you take the other part, the other reduction rule, then you go to n boson system, you do the reduction rules, and you end up with the excitation spectrum of an even nucleus which is adjacent. Yeah? It's sitting next to the odd A nucleus. In the case of a dynamical supersymmetry, the important point is both are described with one Hamiltonian, which means that both are described with one parameter set. Yeah? Independent whether you have the fermionic part or the bosonic part. And this one parameter set creates, for instance, here the bosonic Hamiltonian, but it creates here the bosonic Hamiltonian, the fermionic part, and the boson-fermion interaction. So from symmetry concept is very nice. Question is, of course, whether it's realized in nature. And so we have now to look where such concepts can be applied. Now, this is the Carsten or symmetry triangle. Blue are vibrational nuclei. Yellow are the color index for rotational nuclei. Red is the color index for gamma unstable nuclei. And so in the middle of the shell, we have the deformed rotors, so SU3 nuclei. Then at the edges, near to the closed shells, we have the vibrational nuclei, here also, vibrational type of nuclei. In between, we have transitional nuclei. And on this side, because here we go in this way to the rotor, but here we go over the O6 region to the rotors. So if you look at the color codes, then we see good candidates for O6 symmetry are platinum, osmium in this region. And now for the spin 6, we need an O6 core and a 3-half fermion. Now if you look at the proton orbits, then the highest one is S1 half. But if you are in tin, then you have already completely filled the S1 half orbit, because you can only make a 0 plus out of S1 half. And there are only a 1 half and then 0 plus and it's finished, it's full. Then we have a D3 half, which needs to be filled in the platinum osmium region. So that's a good candidate, because it's isolated, because it's followed by the unique parity orbit, H13 and the other positive parity orbits are much more lower. So we have a filled 1/2 orbit, we have a quite isolated 3-half orbit, and we have an O6 core. So it turns out that we will try the iridium isotopes and the gold odd proton isotopes. In fact, the first example, which was published by Bas Ballant in Iakello, is osmium 190, calculated with the 4 parameters of the model, together with iridium 191. Now, the plot is a little bit complicated. I think you can study it more when you get the slides. So the full lines are experimental lines. The dashed line with small dashes is if you do a pure O6 fit to it. So it means you determine separately the parameters for the even nucleus, and then the longer dashed lines are the results of the supersymmetry. And of course, you see that the fit of only O6, only to osmium, is better than the supersymmetry fit, but it's not much better. I mean, the difference here is it's bigger, but here it's smaller. So in general, the fit is as good in agreement if you take the supersymmetric approach, calculating both nuclei with one set of parameters, or here it's the same. So the full lines are experimental. The short dashed line are the Boson-Fermi spin 6 results fitted only to iridium, and then the large dashed lines are the fit of both nuclei together. And of course the ratio, here you have 3 parameters for so many states, here you have 4 parameters for so many states. So if you do the supersymmetric approach, then the number of parameters relative needed to fit the spectra is reduced to 4. So it's reduced a lot. So this was the first example. We now go to the pseudospin solution. So in this case, we are dealing with U612. Again, we have SO6 for the core. So we are again here in this platinum osmium region. And now we look at the neutron orbits. And we are very lucky because here you have for the neutrons P1 half, F5 half, P3 half. Again, the unique parity orbit, and then it continues with H and F. So again, here we have negative parity orbits, which are quite isolated and which fulfill the space which we have to use 1/2, 3/2, 5. So again, I recall in this case the Hamiltonian has 5 free parameters and 1 constant contribution, and you have an analytic expression which can describe both nuclei. Now, as a case study of this U612 symmetry, the SO6 limit, I will now consider platinum 195. So that's odd neutron platinum. So the energy expression is given here for the odd A nucleus. Then you have this 2-valued expression. You have 1, 2, 3, 4, 5 terms. And of course, in the even, there is no difference between L and J. So D plus E sum up, and we have here L plus 1. You still have O5 and O6, but also here you only have this A and N plus 6 because you don't have this 2 values. And that becomes then a constant because all states in the even have the same value of n. Now here is a comparison to experiment from Mauthofer et al. 1986, and you nicely see experimentally And this is experiment, this is theory, this doublet structure. 1/2, 3/2, 5/2, 3/2, 5/2, 3/2, 1/2, 5/2, 7/2, and so on, 7/2, 9/2. And so it was possible to find many states in platinum 195 belonging to the U612 symmetry, and then the associated even nucleus is 194 platinum, and also there the agreement is reasonable, taking into account that this is a common fit of all these nuclei, both nuclei and all these states. There were some assumptions. I would like to take your attention to one assumption here. Experimentally, one knows that this is either a 1/2 minus state or a 3/2 minus state. Theoretically, it's interpreted as being the lowest one of a new multiplet with 1/2 minus. The second thing, which is important, as I said, odd A nuclei are difficult to study, so we have other levels. These are all the excited states of which the energies are known, but nor the spin nor the parity is known. So that's of course a problem, and you'll see also if you go up in the theoretical spectrum, there are many states which cannot be associated with these observed states because of lack of knowledge of spins and parities, or transfer reaction amplitudes, or electromagnetic decay.
I have a question.
Yeah.
How we can associate sigma and tau quantum numbers to the experimental data?
I will come to that. Yeah.
Okay.
We have to use, of course, not only energies. Yeah? And for the lower states, here below 500, there were a lot of determinations of lifetimes and electromagnetic transition rates. Just take the upper case, for instance, PE2 values between states were measured. And of course, in our model, the PE2 operator has now a bosonic part with a boson charge and a fermionic part with a fermion charge. And so now there are selection rules due to the tau quantum numbers and the sigma quantum numbers. And so if you look in the theory, you see the selection rules. There are many theoretical transitions which are forbidden. Then there are transitions which are large, so they are allowed. And so this is exactly what you use in order to determine precisely the tau quantum numbers. Yeah? This experimental observation, the selection rules, like you would do in an even event. And if you now, let's go through the table. You see, experimentally, those are big and almost equal, and that's also what the theory gives. Those are small, you always expect some graphs. Those are reasonably big, and also in the theory they are reasonably big. Those are again small, those are big, they're not zero but smaller, and so on. And so in general, the agreement is good. I want to point out there is here a problem. There's one transition which is very discrepant with the data. But it's only one. The next ones, for instance, are very well in agreement with the data. Big is big, small is small. So that's one thing you use in order to associate states to the experimental levels. The second thing you can do is, of course, measure G factors and compare the G factors with the data. So then you would need this magnetic operator, and you have here the data. These are the points. For symmetric combinations, these are the ones which have n1 and n2 is equal 0. Or non-symmetric combinations which have n2 non-equal to 0. And again, the agreement is reasonable and general trends seem to be described. So that was the status in the 80s. Now, for about 10 years, or it's even longer, New experiments were done on platinum-195, and especially one particle transfer reactions were performed. And now, what is a transfer reaction? It's a reaction which happens more or less at the perimeter of the atomic nucleus. Yeah? So you have, for instance, a proton, and you shoot the proton on the atomic nucleus, and here you have the valence nucleons. And blue are neutrons, like always, and red are protons. So you can imagine that now this proton picks up one of the neutrons at the periphery. And so they bind and they become a deuteron. And so you have a reaction which is a PD reaction, transfer reaction, which is called of the pickup type, which transforms an even-even in an odd-A nucleus, or an odd-A in an even-even, by removing one neutron. Now, in transfer reactions, you have a lot of observables. You have angular distribution, so you look now how many neutrons are coming relative to the direction of the beam. So the beam direction was like that, and you look how many neutrons are given at a certain angle. And this cross-section, as a function of angle, is described, geometrical properties of it, is described by this Thorne-Born wave approximation, calculation. But then there is another part. This is a kind of reaction part, or geometrical reaction part. The other part is how likely was it that we had this neutron in this orbit. And this is described by what is called the spectroscopic strength, G, for the transfer of a nucleon with a J in L as orbital angular momentum. And that gives the experimental cross-section. And so important is that from the experimental angular distribution, knowing this part from the distorted Born wave approximation calculation, you can extract now for each level its G factor, spectroscopic strength. And this spectroscopic strength is proportional to a factor, which depends on the type of reaction, stripping or pickup, and then the spectroscopic factor, S. And the spectroscopic factor in the theory is just the reduced matrix element squared of a transfer operator. The most easy one is the creation of a fermion. On the initial state, for instance, in the even-even nucleus, and the final state in the odd-A nucleus. Divided by 2ji plus 1. And that, of course, you can calculate. You just now you did calculations of PE2 values, then you take the initial state and the final state in the same nucleus, and you have the transition operator, and you let it work on the wave functions, and look to the overlap of the wave function of the final state. Now you do a calculation for an even-even nucleus. You take these wave functions, you act on it with, for instance, a fermion creation operator, and you do the calculation for the odd-A nucleus, and then you take the overlap with the states in the odd-A nucleus.
May I ask a question?
Yeah.
Are there influence of projectile proton? Are there influence of proton angular momentum? Angular momentum
No,
proton.
it's put in, of course, which energy the protons have and so on. Yeah.
It's this differential cross section is, I think, it's integrated over the energy.
Yeah.
It's not doubly. It's not the sigma the theta the A, but it's integrated over the energy, so it's the sigma the theta.
Yes, of
It's
course.
just not for the O energy,
it's-
for the O momentums.
All the
The
moment.
energy of the protons and everything is in the input of this calculation, for sure.
One
Yeah.
question. Usually, how we calculate the value of the dBWA approximation is just
There are codes called DWG
okay.
who do it. I know they have a horrible number of parameters,
But
but they are studied in over many years. There are optical model parameters and all kinds of things.
But it doesn't matter that we are working, for example, we can determine the spectroscopic length using group theory, and the another model
Yes.
has another
Yeah, no, so what we do,
quantum numbers, therefore
yeah,
I guess that
we use the dynamical supersymmetry to calculate these matrix elements. But still, the problem is we need to describe the reaction mechanism and dynamics and things like that.
yes,
And for that, there is a separate code.
yes.
And then we take these values, we multiply that with these values from this code, and then we can compare two experiments.
Okay.
Yeah. So that's how it's done. Okay. Now, experimentally, this is also a challenging thing. I think you saw VAMOS here, right?
Yeah.
This magnetic spectrometer. So this is the Q3D from Garching in München. And this is also such a magnetic spectrometer. So they are gigantic things. Here you see, that's 1 meter. Yeah? So the whole thing is about 7-8 meter long. And you have to measure angles. So the whole thing, here is the beam coming, here is the target. And so you could have to rotate the whole thing around the beam direction. And of course this weighs tons, but it's possible. Now what happens? You have a quadrupole magnet and then you have 3 dipole magnets, and they make that the particles which are emitted with different angles with the same energy are focused on this focal plane, and the focal plane is inside the detector, so that you can reconstruct it afterwards. So you have a focal plane detector consisting out of wire proportional counters. So you have here also a single wire proportional counter. Then you have segmented detectors which allow you to reconstruct by the deposited charge in these strip detectors here. For instance, here this strip is read out separately from this strip. If it's in the middle, then everything is in this strip. If it's on the side, then you have some charge here and some charge here. Then you have multi-wire proportional counters, and by this you can now reconstruct. At the end, it ends up for a total energy in a scintillator detector. You can reconstruct the way, the path of the particle, its energy, and which kind of particle was passing, because you can have also DT reactions. It picks up 2 neutrons, or DP helium-3 reactions, and so on. So that you can do as a function of angle, and with an extreme good energy resolution. So as I said, you identify the particles, you identify the tracks so that you can reconstruct the focal plane, and then you can cut through your detector at the focal plane and obtain the spectra of the neutrons, for instance. Here you see such spectra for the platinum PD reaction, where you start from 196 platinum and you end up in 195 platinum. Now be careful, this is a logarithmic scale. Yeah? This is 10 to the 3, this is 10. What you observe is you have very nice spectra with very high resolution compared to the energies of the proton. So the resolution is about 6 kilo electron volt, but the energy of the protons is about 20 mega electron volt. So that's as good as you can do. You have no background between the peaks. The background is non-existing, and you see the height of the peak varies quite a lot, and that is of course reflecting that the spectroscopic factors for different states are different. Now, from the angular distribution, you get the parity and orbital angular momentum of the transferred neutron. This is of course model space relevant information, but of course only with this information you cannot distinguish between a P1/2 transfer or a P3/2 transfer. You can measure whether it's a P or an F nucleon. So also between the F5/2 and the F7/2 in such a simple angular distributions you cannot distinguish. However, there is a way out. It's more complicated. It's to use polarized beam. For instance, suppose I have platinum 196 and I have polarized deuterium, which makes the neutron pickup is a DT reaction. Yeah. Now, unique spin assignments can be obtained by polarized transfer. Then the cross-section becomes sensitive to the orientation of the spin in the transferred particle. Yeah. If you have P3/2, then the spin is up. If you have P1/2, then the spin is down. And while in the case for the angular distributions, you don't see a lot of difference here for P1/2, which is a full line, and the dashed line for P1/2. If you take the analyzing power, which is defined as the cross-section with spin up for the beam minus the cross-section with spin down for the beam over the sum of the cross-section with spin up and spin down, then they clearly separate. This analyzing power is positive for the ones which have spin up, like P3/2, and negative for the ones which have spin down, like P1/2. And here you see the fits to this analyzing power. You have a very well description. And the same holds also for F5/2 and F7/2 or H9/2 and I13/2. So you can, using these polarized beams, you can determine the spins and the parities in a unique way.
Sir, I missed
Yeah.
somehow. So how we can obtain this polarized transfer? This polarized.
This A.
Yeah, I somehow missed that.
Yeah. So what you do first a beam, let's say with spin up. Protons are coming polarized with spin up.
Mhm.
You measure the cross section, and then you do a beam where you now invert the polarization. Now the protons are coming with spin down. Yeah. And so then you take the difference of the cross section with spin up and spin down. To normalize, you take the sum of both. And then it turns out that if the spin was down, then this quantity will be negative. If the spin of the neutron was up, so it means P3/2, then the quantity will be positive.
Maybe you can ask, but for example, if you have your spins of the beam oriented, what about the spins of the target? Shouldn't you?
No, they are not oriented.
Okay, but so you have a spin coming up, and you don't have any idea what's the spin of the target.
Yes,
So you have.
but statistically there is an effect because the interaction when the spin is up and the spin is down is not the same. That's
No,
in
no,
essence.
isn't the interaction dependent on the relative spin of the target and the beam?
Yes,
But the target is not orientated.
yeah, but you, I mean, let's say spin up interacts more with spin up. Yeah.
Yes,
So the target is not oriented, but have 50% spin up and spin down.
yes.
But then the cross section here will be bigger
And
for those which have spin up. If this is a P3/2, it has spin up. And if I come with a spin down, to it. So the target does not need to be polarized. If you have a polarized beam, it's sufficient to get an effect.
yes, not as strong as if the target is for.
No, it would be much stronger if the target is polarized. Yes.
Yes.
Yeah.
Just statistically.
But it's difficult to polarize a target. It's already difficult to polarize the beam. Okay. Now using this data, these are the old data. They were in fact measured by GSI, And these are the new data from this new experiment, which has now the 5 parameters. And first of all, let's look at the experiment. You see, up to this energy, all these spins are uniquely determined. So it's amazing, and the parity also. So they are, from this transfer data, and of course from the previous data, we have a unique determination of a very complex of a nucleus up to an energy of about 1.5. And so you have all these beautiful multiplets, which are compared here to the theory. And you see there is an amazing good agreement. Now, of course, you may say, yeah, that's because you do color identification. Yeah? This is indeed true, but it's based on these PE2 values, these magnetic values I showed you before, and on the transfer amplitudes. So here you see the comparison of the transfer strengths extracted from the experiment with theory. Now, the easiest transfer operator is, remember, this was the real fermion, and in this experiment I take a real neutron, yeah, a real fermion. So that had the symbol C, J, Decker. The first approximation is, well, my model fermion is the real fermion, so I take only A Decker J and calculate the reduced matrix amount. But that's not true, and microscopically it has been worked out. The next higher order term is this one, which is already with 3 different operators, and then the next one is this one with even more, the same number of operators. So this you see in the calculation by Jose Barea from Mexico. Is he still in Mexico?
No,
Chile.
Chile,
He's in
yeah.
Chile. Okay. But he's Mexican.
In Spanish.
Eh?
In Spanish.
No, it's true, he was a student of Clara. Yeah. No, he's Spanish. Anyhow. Physicists in the whole world. He was in Köln, also. So here you see the results of the experiment at the bottom, and of the calculation in the first order approximation only this, second order, and then third order approximation. Be careful, this is a very highly logarithmic scale. So there are 5 orders of magnitude here. And in general, there is good agreement between the measured transfer strength and the observed transfer strength. So this is one possibility to confirm the quantum numbers which are introduced in the previous plot. So this is kind of experimental additional information which is used in order to assign this quantum number. Finally, to conclude this lecture, I would like to say something on the supersymmetry.
So,
Yeah.
excuse me. So, the previous
Yeah.
figure, in the previous figure, so number of peaks of experimental
Yeah,
data,
it's higher than the number.
yes, theoretical
Yeah.
peaks.
This is also what you would expect. So some of these peaks are very small. They are 1/100th of the biggest one. It's 1%. So that's, you have to be a bit careful with the scale. Yeah? So if I look at, these are limits, experimental limits of peaks. But the overall agreement is overall good. If you go to the details, then you have some discrepancies at higher energies. Yeah. Now, but I still have 5 minutes. So supersymmetry without the analytical symmetry. In this U612 supersymmetry, you don't, in fact, need to have an analytic solution, because this is sitting on top of it, and we will see an example in the exercises concerning IBM2 that because it's sitting on top, supersymmetry can hold, independent of whether you can construct a dynamical symmetry. So that means you can now work with this Hamiltonian, which has all the terms, and describe simultaneously even even and odd A nuclei which are transitional. So there is an example. These are the ruthenium-rhodium isotopes made by Alejandro Frank and Piet van Isacker and the former Dave Warner. And so they parameterize as a function of n some of the parameters. Here, you see here also, all in keV, so that they have, and at the end they have 1, 2, 3, 4, 5, 6, 7, 8 parameters. And with that, they describe a whole series of combinations of negative parity made from the I 13.5 and the hash 12.5, which also leads to negative parity states. So that was the situation in 1989, and the theoretical prediction for 196 volt. And it took about 10 years to verify this prediction. Now the first thing to do is transfer reactions. Because the DT reaction, so you shoot with deuterons and you get tritons out, so you have transferred one neutron, were performed on gold 197. And what you see here is the experimental spectrum. From the angular distribution, you can determine which states are negative parity and which states are positive parity. And so here you have the measured negative parity spectrum. Ground state is here, and then 500 MeV is here. And indeed, we see many peaks, indicating that there are many still unassigned or unobserved negative parity states in gold 196 below 500 MeV. Now, because spectroscopic factors could not be extracted from this experiment, what we have done, we have convoluted at a certain angle, 15 degrees, our theoretical values with the dBPA calculations, and so from the calculated spectroscopic factor, we can now generate also a theoretical experimental spectrum. And the next thing we can test is we go in energy from 0 up to 1000, and we make a running sum of the experimental values, summed values of the spectroscopic strength, and we compare that with the theoretical values of the spectroscopic strength. One problem is there were not enough data to distinguish the different orbits. Yeah, that we made this running sum. Now the conclusion was that although the spectra look a little bit different, the running sums are very similar. They go up to 500 and then they saturate in theory. You have some graphs adding up, but it's maybe 15% of what you see here. And also the onset is very similar. In 1993, Orsay experiments, the other one was in Garvey, allowed to distinguish between L equal 1 and L equal 3. Yeah, so here experimentally you could now see these states have L equal 1 transfer, these states have L equal 3 transfer. If you compare it with supersymmetry, you get this value. So that's not very well described if you compare it like that. But you can try to break supersymmetry. That was tried by moving this 1 minus state higher up to here. So you break supersymmetry and then you get a better description of the data. However, the resolution in energy in Orsay was not very good. So the point is that these states, which are in disagreement, or the non-occurrence of this state, can be due to doublets or triplets. And so you measure a strength, but you're measuring the strength of two states, which are very closely spaced, instead of one state. So In order to do that, new studies were started on gold 196 of the same type as I told you before, so transfer PD, and then also with polarized beam. But now on the odd nucleus, towards the odd nucleus. Again, we use the Q3D spectrometer in Garfield with its amazing energy resolution of 6 keV. We were able to show that indeed the ground state in the transfer experiment is a doublet. And the doublet has a spacing of 6 kilo electron volt. Yeah? So that could not be resolved in ORCE. And we saw many more new states forming doublets in the original transfer experiments. They are all given here in red boxes. So all these red box states are resolved doublets in this beautiful transfer spectrum, where again the background is 0 in between the peaks. Okay, it's 10, but here we're talking about 10,000 counts. Yeah? And we did also the polarized experiment, which allows you now to get the transferred spin. So you can determine from this analyzing powers whether it's a combination of P or 3/2 and so on. So we have the neutron transfer as P1/2, P3/2, F5/2. So we can determine whether it's P or whether it's a mixture of different orbits. Now, why is this important? The situation is a little bit more complicated in this case, because we start from an odd nucleus which has a spin 3/2 plus. Experimentally, we can determine what is the content of the transferred particle to a state. Let's take one example. If the final state is 2 minus, then the transferred intensity can contain one part of P1/2, one part of P3/2, and one part of P5/2. They all can make a 2 minus state. If the transfer is pure F5/2, then we can argue that most likely we are populating a 4 minus state. Yeah, because this cannot be populated by the other ones. If the transfer is purely P3/2, we can argue that this is most likely a 0 minus state because it doesn't show the other transfers. If it's only P3/2 and F5/2, we can argue that this is most likely a 3 minus, but if we observe also a P1/2 component, then we can argue it's 1 minus or 2 minus. And also in the data you see here you have different contributions. You don't have pure transfer necessary. In order to solve this problem or to try to find out that the thing is consistent, a very difficult experiment was done by the München group. This was using a transfer reaction in which the final particle is an alpha particle and you start with a deuteron on an even nucleus, which is 198 mercury. Then you don't have this problem because the even nucleus has a 0 plus ground state. If you measure the art of transfer particle, you know at the end you can determine the spin uniquely. Also because alpha particles have spin 0. Yeah, it's also a spin 0 particle. The price to pay is the intensity. You see the maximum reduced from 10,000 to 100. The second problem is the energy resolution, because you know that the stopping power of alpha particle in material is very big, and now you have to get the alpha particle after the transfer reaction out of the target without too much loss of energy. So that's very difficult, so you have to use very thin mercury targets. but still you have some energy straggling, but now you know from the PD reaction where the states are, for instance here 0 and 6 keV, they form a kind of potato, but having the knowledge you can fit a boat in a double peak fit and extract from that the transfer strengths. You can do it to make it even more difficult using polarized beam. And then you see here the spectra with spin up and spin down is in red. And you really see that there are large changes. Look at these two peaks. It's reduced 50% with spin up. It's increased or doubled here with spin up. Yeah? So from the spectra you see here also clearly different behaviors. And that's of course very important information in order to extract knowledge on the states. Now, here are examples of the cross-sections for different states and the analyzing powers for different states here. There are cross-sections analyzing powers. Now, you have a ground state of 0 plus, and then you have, of course, that the deuteron has a spin 1. So you have to combine the deuteron transfer with the nucleon transfer to a total J transfer, and then you end up in a state with J and parity minus L for the transfer. Now it turns out that in the combinations you can work it out, and you can get 17 safe spin assignments from this experiment in 196 volt below 500 keV. More states are observed, but we cannot do this for all states. And because of that, you can test your hypothesis which you used before, and you can fix some spins and parities using the alpha, big D alpha reaction. And this is the outcome from the experiment. Before known was only a 2 minus ground state. And now we know it's a 6 keV doublet of a 1 minus and a 2 minus. This is the original prediction, 1 minus, 2 minus, so that's very good, in fact. Yeah? Although it looked worse, it's very good. And then these are the up to 600, 700, experimentally up to 600. We observe many states. New of negative parity, and we can assign for many shore spin and parities. Some are in brackets still, but many have unique spin and parity assignments. And in order to test this, of course, we look at the transfer reaction amplitudes, strengths here as a function of energy for P1 half transfer, P3 half transfer, F5 half transfer to 1 minus states. These are the 1 minus states. The same here for 2 minus states, same here for 3 minus states, where you cannot not have a P1 half transfer. What you see here are the experimental values compared to the theoretical ones. And so it's possible to identify more or less many of the states, so you can assign the quantum numbers of the states. You see these dashed lines, that's how the states are identified. So as I said, this work took about 10 years, the verification of the original prediction. Now, at the same time, you can do in-beam spectroscopy, in which you now do another kind of reaction, a fusion evaporation reaction. So, contrast to the direct reaction, the proton is captured, for instance, stays up to 10 to the minus 16 seconds in the compound nucleus, and then some evaporation, for instance, of a neutron is happening, and you get then the de-excitation by conversion electrons and gamma emission. Now these in-beam experiments were done at 3 places. We measured gamma rays and conversion electrons. Conversion electrons are very important in heavy odd-odd nuclei. Yeah? Mostly transitions go by conversion electrons in many cases. And that we did using the D to N reaction at the Philips cyclotron of the Paul Scherrer Institute in Switzerland. And we used for the PN reaction, which has a higher, a smaller cross section. No, PN has a higher. Okay. Anyhow, this was used at the Bonn cyclotron and at Yale, at the then still existing tandem accelerator, using the IRAS path. So here you see examples of the PN reaction at 9 MeV. I'm wondering, I think this should be, no, this is a small cross section. This reaction has about 1 bar cross section. Now why we use this cross section? Because side reactions like P2N or DN or D3N are not populated. And so you get very clean spectra. If you go to a higher energy with a higher cross section, then you see here P2N reactions become dominant. Yes. So you have to well choose your energy. Here is an example of conversion electron spectra, and you really see that this conversion electron spectra, as a function of the momentum of the electrons, show many peaks, because we are dealing with odd nuclei. Now, the results for the lowest state from the in-beam work, and again, you cannot read it, but the highest state here is 405 kiloelectron volts. Yeah? So you see there are enormous amount of states, there are an enormous amount of gamma ray transitions, which you have in such an important system. So that's the result. Further results, and what we found, we have 53 states under 100, 800 TeV. 10 new states were observed in the in-beam. 300 transition, spin and parity limitations by electromagnetic decay could be determined. So that was there was one PhD by Alexander Metz on the transfer experiment, was one PhD by Jochen Gröger on the in-beam work. So the final result, as a function of the 6 parameters, you have a dynamical symmetry, so every state in the 6 nuclei has quantum numbers. And so this is the final result. On the same scale, in the even nucleus, of course, we took more states higher up. But just to present the increasing complexity when you go from the even up to 800 keV, to the odd neutron, to the odd proton, and to the odd nucleus. So we could describe this with 6 parameters, mainly as a prediction. The prediction changed because we found out, I didn't mention that. I mentioned that in platinum-195, in the old fit, an important state had spin 1/2 or 3/2 minus, and it was taken in the theory to be 1/2 minus. From our transfer experiments, we found out that the spin is not 1/2 minus, but 3/2 minus. So we had to adapt the fit again, because this level is important to determine some of the parameters. I will come to that. So more transfer reactions experiments have been done since 2000 into 196 gold. One is you do proton transfer from platinum 195 into gold 196. This is a 3 D reaction. And the interesting part is because, platinum has spin 1/2 plus, and so we now transfer S1/2 D 3/2, and D 3/2 is what we have in our symmetry, U64. We don't consider the S1 half orbit. And so by doing this transfer, we can now also extract S1 half strength in order to test whether our restricted model space is valid. And this is what you see here. As a function of energy, again as a running sum, the strength for P 3/2 going like that, and then saturating here as we saw before, and the strength for S1 half, and you see it's small, even more or less continuous here, and then suddenly at 900 keV it suddenly increased and becomes important. Yeah. So it means that the breaking more or less of the S1 half coupled to 0 is only important at high energies, much more higher than we compare the theory with the experiment. Nevertheless, these small contributions were important because they, of course, help to limit the spin values, starting from 1/2 initial spin. It can only populate 0 or 1. Now, also, the other reaction, alpha D, was done from 194 platinum to 196 gold by Wirth and Friedrich Wirth et al. And now we start again from an even nucleus into the odd nucleus, and the transfer reaction now using an alpha beam had only a cross section of 5 microbarn, so it's very, very difficult reaction. And the final result of all these experiments is here given. So some of the things which were in brackets are not anymore in brackets. I think one state changed spin, and so we now compare that with the theory, and 21 out of the 27 states have now safe spin assignments below 500 keV. Now, as I said, the essence is that it's a prediction from supersymmetry, and so we have to look at the parameters A, B, B prime, C, D, E, describing all extracted from 3 nuclei and describing all 4 nuclei. The prediction in 1989 were these values. As I said, an important state changed its assignment because it was wrongly assigned in 1989, and so that causes here these changes from 62 to 51, from -2 to 7. And the final result in 2000 is very similar to the prediction. There are some at the LL and JJ level, there are some changes, but it's very small. So this is without and with gold planet. The total number of states described by the 6 parameters is 8 in the even, 43 in the odd A, 27 in the odd. So 43 plus 8 is 51. That makes 51, 78 states. Described as 6 parameters in 4 different mediums. Yes?
In the previous slide,
Yes.
you only have it on the proton in the 3 half state, right? You have not included the S1 half state.
No.
That's why the fact
No, this is without the S1 half. But we have used the S1 half to fix experimentally spins, to limit spins. So that's what I mean. Although it's not in the model space, it's still useful.
But that's why the 5 half, 1 half state is not split, right?
Yes, yeah. It's still, the theoretical calculation is only considered a D 3/2 proton. Yes. But to describe 78 states with 6 parameters in 4 different nuclei is certainly an achievement, and that's why I call this the golden gold platinum region. So we have these quartets which we have investigated. One doesn't work so well, but this one with 196 gold works quite well. Now, can the quartet be extended is the question. In principle, yes. We can now transform another boson into a fermion, and so then we have considered the case where we transform 2 proton bosons into 2 proton fermions and couple the 5 neutron bosons to it. Now there is an ambiguity which unfortunately does not exist in this region. If I would do it for the neutrons, then I would have a description of an even nucleus as a function of neutron bosons and then 2 neutron fermions. So the question is, can you do that? Because you treat some paired nucleons as bosons and some as fermions. So maybe these are higher lying broken paired states. Now in the case of mercury, this does not occur because this is a closed shell, thin, and if I take a fermion calculation, I can couple 2 fermions to a closed shell, proton fermions to a closed shell, and describe the normal excited state spectrum. So that's why we can use now, here we now have 2 fermions, and we can couple the 2 fermions to U6-4 symmetry, and calculate then all these reduction rules, and we will describe not gold 195, but mercury 196. So also here experiments have been done, alpha to N in Köln, and also using Iris Bell in Yale. This P3N reaction and followed by beta decay to 196 gold. And for 198 gold, both reactions were done once again, fusion evaporation and beta decay experiment in Köln. This formed the PhD thesis of Christian Bernards in 2011. So the theoretical prediction you obtain now in 2 proton fermions coupled to 5 neutron bosons is this one. And you see you have this kind of mixed symmetry states here, but now they are formed using explicit neutron fermions. And this is a result of the experiment. It's not really in an extended supersymmetry description anymore, because there are more and more vibrational characters, because you're so close to the lead isotopes. So I was wrong before, it's lead isotope, not tin isotope. But nevertheless, you could do a calculation with 3 parameters describing mercury in the extended supersymmetry. This is the case for 198, mercury, also 3 parameters, and you have this reasonable good agreement between theory and well-known experiment. Still, there are some uncertain spin assignments here, also here. These are candidates for this kind of mixed symmetry states experiment. This 4 and this 3.
So
Yeah.
somehow, so you have your model predictions. For example, you have some number of proton bosons
Yeah.
and some neutron bosons, and let's say 1 fermion left. Protons, for example, you might say, okay, I don't like the IBA approximation is not so good. Let's break one of the pairs.
Yes.
And treat them as not as a boson but as 2 fermions.
Yes, but that
But this game does stop somewhere.
no, that is done. This kind of broken pair calculations in even. But they correspond to this kind of excited states at higher energy because you need some
You need
energy.
to break a pair so you can
Yeah,
evoke
yeah,
in
yeah. But in this case, there is no ambiguity because you're a closed shell for the protons. So they are considered, in fact, it has been done in detail by Vretenaar before he started relativistic calculations. And he wrote the code in order also to describe high spin physics using these proton pairs. But it was not used extensively by experimentalists, so he went into another field, relativistic calculations. Okay. Now you can invert it and you can go back and look at the predictions from the fit of 196 mercury for 195 gold and 194 platinum. And so here, these are the theoretical values, these are the data. So we fit here 196 mercury, and then you look at the predictions for the other ones. And you see there are some problems, especially here the splitting, which you predict is much too small compared to the data. So it's not really an extended supersymmetry anymore. There's another example which was studied by Valotus and the München group, and also worked on by the Mexican group around Rudolf Weiger, quite a lot, by Barea, which is iridium 194, which was measured by Valotus. This measurement took 20 years. Our measurement took 10 years, but this analysis, I'm sure, took 20 years. And so what comes out of this experiment is here the experimental level scheme shown here. You can look at the details if you have the slides. And this is the calculated level scheme using extended supersymmetry. Also, the agreement is good, but there is a hic to it. This is the experimental 193 iridium, that's also good, calculated one. Also using a 6-parameter Hamiltonian. The problem is not in osmium 192. There you have also quite good example of O6 symmetry. But the problem is in osmium 193, because the experimental level scheme is here, and it starts with a 3/2 1/2 doublet followed by a 3/2 5/2 doublet, while in the theory oh no, I'm going in the wrong direction.
Yeah.
While in the theory the ground state is a 1/2, like U612, and then there is a 3/2 5/2 doublet and a 1/2 3/2 doublet. So it's not what is seen in the experiment. And most likely this is because this nucleus is becoming deformed. And so the O6 condition underlying the model is not anymore fulfilled. Nevertheless, it has to be said that the transfer strengths for the platinum to iridium 194 reaction are very well described in the model. So here you compare calculated transfer and experimental for different states, and there is a good agreement by the transfers. This presents the, again, complicated experiment, polarized neutrons and alpha go out from an even into the odd nucleus. You see there is a wealth of data which was measured in this nucleus by Hans Friedrich. So I will finish a little bit earlier than normal. I come to my general conclusions. Symmetries, whether they are dynamical or fundamental, are an essential tool to guide us through the complex behavior of the atomic nucleus, or I could easily say to the physics in general. So they are tools. Important is they provide benchmarks and robust predictions which experiments can directly verify or falsify. And I would say this is why experimentators like Rick or I, we love them. Because it's clear. If you have a selection rule, either you do the experiment and the selection rule is fulfilled or not. If it's fulfilled, the symmetry is probably not so bad idea. If it's not fulfilled, tant pis. That's the French say. It's not so that you have to go to a theoretician and you say, these are my experimental data, and then he does a calculation and then he has agreement with your data or less agreement. Here it's always clear before. Either I measure it and it's okay, or I don't measure it and it's wrong. Symmetries are important also because they lay the basis for further perturbative treatments, refining our understanding of it. There was one question in the lesson of Marc Caprio, why the Davidson potential? Because it's such a phenomenological thing and not microscopical. Now the Davidson potential has the advantage, it's a complete solution. It has a complete basis. So that means that you can then do more performant calculations, and in fact that is what David Rowe does, using the Davidson basis states. Yeah? And so always if you get an analytic solution and you do the reductions, you have a complete basis. And then you can define any numerical microscopically based Hamiltonian, like in the IBFM calculations, and use this basis to diagonalize this more semi-microscopical Hamiltonian. So that's an important point. They provide understanding of complex situations. Nobody can read a wave function of a large-scale shell model calculation. I had a student and she did large-scale Antoine calculations. And I was always asking her, can I take a look at the wave function? And she never said that I could take a look at the wave function. So I thought, that's it. Then finally, she confessed that the output of the calculation were 1000 A4 pages. And that the largest components, I think, in the wave functions were a few percent or something. But then it was several. So it means that these wave functions of large scale shell model calculations you cannot read in your lifetime to the end. Yeah? So in order to provide understanding in complex situations, you have to try to make sense of it, and this is often by using these simpler symmetry-based models. Of course, at the end, you would like to have the large-scale shell model answer also to compare with the data. But then the interpretation goes easier if you have these simpler models. And in fact, people doing very difficult theoretical calculations with density formalism or large-scale shell models over a coffee, they agree that they also use the language of the simpler models in order to interpret their results. They urge experimentators to adopt new approaches in order to get the unreachable but crucial while robust numbers. So this is, one example is in Norbert Pietrala's lecture. There were these predictions of mixed symmetry states, and nobody had observed them. So till Achim Richter in 1984 observed the first 1+ mixed symmetry state. The Gold 196 case is also an example where you really, as experimentalists, have to use the best methods in order to extract crucial experimental observations. They should be provided a solid microscopic foundation by comparing their predictions with those of more microscopically funded models. Here also I discussed possibilities to determine the parameters from a microscopic basis. One was to use the shell model and to do a mapping on the interacting boson model. So then your parameters come from the shell model calculation, but you can only do that in spherical nuclei. If you have deformed nuclei, then there is new on the market and available here in Ganil another method elaborated by Kosuke Nomura from Tokyo. So you use the density formula or scarum interactions. They calculate these potential energy surfaces, and then you fit, or you calculate in the IBM, two also potential energy surfaces, and you fit them to each other until they fit, and then you have the advantage that in the IBM everything is coupled to good particle number, good angular momentum, and so on. So you get immediately the excitation spectrum and the transition rates and so on, which is difficult in the other formalism to achieve. So new symmetries like supersymmetry may offer even new ways to unify our understanding of nuclei. Now, summary of symmetries over the years. Immediately after the discovery of the neutron, Heisenberg proposed isospin, which relates the proton to the neutron, and say it's just a nucleon with the isospin 1/2 up and down. Wigner, in 1936, extended this isospin to a spin-isospin combination, SU4, in which you have now a considering of a higher symmetry in order to unify the nuclear forces. In 1947, Racah introduced seniority, or introduced the description of pairing. So we saw that seniority has to do with the number of, for instance, d bosons not paired to 0. In 1948, Meyer and Kuppertmeyer and Jensen introduced the spherical shell model, which also has a lot of dynamical symmetries in it, which are used. Then, in 1952, Bohr and Waddelston introduced the corrective model, which has these octahedral symmetries, these reflection symmetries. So it's not dynamical symmetries, but kind of reflection symmetries, but also the Wigner matrices are related to angular momentum. In 1958, I don't know whether Pete talked about it, there was a big step forward because the shell model and the collective model were opponents. Yeah?
I will discuss it on Monday.
On Monday. And then Elliot showed that you can get rotational spectra in a pure shell model calculation. So you get a connection that shell model and collective model are not opponents, they are somehow related. But people discuss that on Monday. Then what I discussed was from 1974 on the interacting boson approximation, where you replace paired nucleons by bosons, as in D, or you have extensions, which I mentioned. And then in 1980, Franco Iacello introduced supersymmetry in dynamical supersymmetry to describe even an odd A nuclear on an equal basis. Finally, I wrote a popular description of his last story, which appeared in Scientific American in 2002. For the German, you have a German translation of this article in Spectrum der Wissenschaften, and so you might want to take a look at it. It appeared in 17 other languages, so probably in your language. I have a Japanese version at least. So the funny thing is, the designer, so you work with professional designers, and so explaining them what we do, that we have neutrons and protons, and we transform them and we connect them, and they are unconnected systems. And so he came up with this picture. So this is platinum-196. This is an apple, and then you have an orange. That's an odd A nucleus, and another golden orange, yeah? And a platinum orange and a golden orange. Here you see the gold. And so you transform them. Because there is an American saying, nothing compares so like apples and pears. Apples and oranges. But in German, the saying, if you translate it, it's not apples and oranges, but it's apples and pears. And so they changed the cover. And made it apples and pears.
What's it in Japanese?
No, that's no. I discussed it. It's something like earth and heaven, isn't it? Not two things are so different as earth and heaven in Japanese. If you say things are different like apples and oranges in English, you know this saying? They are very different. I was told that in Japan you would say nothing is as different as earth and heaven. No? Anyhow, maybe it was in Russian. Or, So again, I will distribute the slides, so they will be available today. And also at the end of the afternoon, we will distribute the exercises and their solutions. Yeah. So with this, I would like to conclude the lecture. Remember, I tried, unfortunately, you cannot download here the Springer book, our Springer book. You cannot, this on symmetries in atomic nuclei. No. But I guess Pete has all the PDF files.
Do I? I'm not sure.
So I
have a copy
of the book. Yeah, also. I have to look. Maybe I can give you the PDF files of the book, so that you can place them on. It's an internal website.
No, it's not internal, so I wouldn't.
I know that. Yeah. But most institutes have access.